Find a clear night, step outside, and let your eyes adjust to the dark above you. The stars will come slowly at first, then all at once, hundreds of them pressing through the black. On a perfect night, with no city light bleeding into the sky, you might count a few thousand with the naked eye. Each one of those points of light is a sun, burning somewhere in the void at distances the human mind was never built to hold. And around almost every single one of those suns, there are worlds in orbit, circling in the dark. Some of those worlds are rocky, some are wrapped in gas, some are locked in permanent ice. Most of them will never be visited, never be mapped, never be truly known by anything with a mind. But a handful of them are so far outside any reasonable expectation of what a planet should be that they demand attention. Tonight, those are the worlds we are going to visit. There are 10 of them, each confirmed by NASA and the leading observatories of the modern era. Not speculation, not theory, not science fiction. What follows is documented, measured, peer-reviewed, and in every case more disturbing than anything a writer could invent. These are planets that broke the assumptions of the scientists who found them. Several researchers, upon seeing the initial data, suspected their instruments had failed before they accepted what the numbers were actually saying. That moment, when a trained astronomer looks at a reading and thinks the equipment must be wrong, is worth sitting with. It means the universe has produced something that exceeds the boundaries of professional expectation. That is the threshold we are crossing tonight, 10 times over. Before we reach the first world, consider what it means for a planet to exist at all. Formation requires gas and dust and time and gravity working together in a process that takes millions of years to complete. The result, in our solar system at least, is a set of stable, predictable, relatively calm worlds. Earth has weather, but it has survived it for 4.5 billion years. Mars has seasons, Jupiter has storms, but nothing in our neighborhood would make an astronomer question their instruments. The 10 worlds ahead exist in a different register entirely. A register where the rules that govern our solar system are not merely bent, but systematically destroyed. They are the universe at its most extreme, and they are real. The first world on this list sits 1,400 light-years from where you are standing right now. It is a gas giant, the same broad category as Jupiter, a planet made primarily of hydrogen and helium with no solid surface to speak of. In our solar system, gas giants live at a comfortable remove from the sun, far enough out that the star's gravity shapes their orbits without threatening their existence. This planet made a different choice, or rather, the physics of its early system made that choice for it. It drifted inward over millions of years, drawn closer and closer to its host star until it crossed a boundary for which no planet returns. Its name is WASP, 12b, and it is in the process of being destroyed. The number that defines WASP, 12b more than any other, is 1. 1. That is the length of its year measured in Earth days. One full orbit around its star takes just over 24 hours. For context, Mercury, the innermost planet of our solar system, completes its year in 88 Earth days, and Mercury is already considered dangerously close to the Sun. WASP 12b orbits in a fraction of that time, pressed so close to its star that the relationship between the two has stopped being planetary and started being something else entirely. At that proximity, gravity does not simply hold the planet in orbit. It reaches into the planet and begins to work on it from the inside out, pulling at its structure with a force that has no equivalent anywhere in our solar system. The technical term for what is happening to WASP, 12b, is tidal deformation, but that phrase understates the reality considerably. Tidal forces are familiar on Earth. They pull the oceans toward the moon and create the rhythm of the tides. On WASP, 12b, the same principle is operating at a scale that has physically changed the shape of the planet. The star's gravitational grip on the near side of the planet is measurably stronger than its grip on the far side, and that difference is large enough to stretch the planet out of its natural spherical form. WASP 12b is no longer round. It has been pulled into an elongated egg shape, bulging toward the star on one side and drawn out on the other. No planet in our solar system, under any conditions, experiences anything approaching this level of structural distortion. What makes this worse, considerably worse, is that the deformation is only the beginning of what the star is doing to this planet. The same gravitational and radiative forces that have reshaped WASP 12b are also stripping material from its upper atmosphere in a continuous, measurable stream. Gas is flowing from the planet to the star right now, a river of superheated material bleeding away into space at a rate that astronomers have been able to observe directly. The planet is losing the equivalent of several Earth masses every million years, not in a single catastrophic event, but in a slow, relentless hemorrhage that has been running for as long as the planet has occupied this orbit. There is no mechanism that stops this process, no equilibrium to reach, no point at which the loss slows down. The arithmetic of that loss leads to a conclusion that is as simple as it is final. In approximately 10 million years, WASP 12b will no longer exist. Not destroyed in a collision, not swallowed in a sudden event, but simply gone, dissolved into its star gram by gram over geological time. 10 million years sounds like an enormous span, and by human standards, it is incomprehensible. But in the life of a solar system, 10 million years is a short chapter, a brief remaining interval before something that was once a planet ceases to be anything at all. The star will continue burning. The orbit will continue existing as a path through space. There will simply be nothing left to travel it. What gives WASP 12b its particular weight as a story is not the violence of its ending, but the ordinariness of its beginning. Before it migrated inward, before it crossed the threshold, it was in all likelihood a perfectly unremarkable gas giant. The same broad type as Jupiter, the same general composition, the same kind of stable existence that billions of gas giants across the galaxy maintain without incident. Something in the dynamics of its early system set it drifting inward, a gravitational interaction with another body, a resonance that pushed it closer and closer until the star's influence became total. At some point, it passed the line beyond which no return is possible, and the planet that had existed quietly for millions of years became a planet with a countdown attached to it. That is the thought that stays with you when you consider WASP 12b, not the egg shape, not the atmospheric bleed, not even the 10 million year deadline. It is the question of what this world was before it became what it is now. A planet that had no reason to expect any fate other than a long, uneventful existence beside its star, until something shifted and the star that had been its anchor became its executioner. WASP 12b is still there, still orbiting, still technically a planet by every classification we have. It is simply a planet that has already received its sentence, circling in an orbit that is also, slowly and without any possibility of appeal, its end. The second world on this list occupies a different category of wrongness, one that requires dismantling a rule most people never knew existed. That rule is simple and feels obvious once stated. Stars are hot, planets are not, and the gap between them is not a matter of degree, but of kind. A planet absorbs stellar energy and radiates it away, always cooler than the thing it orbits, always sitting well below the temperatures that define stellar physics. That boundary has held across every planetary system we have ever studied, across every model we have ever built, across every instinct astronomers bring to their work. KLT 9b does not hold it. KLT 9b is a planet with a dayside temperature exceeding 4,300 degrees Celsius, a number that places it above approximately 80% of all known stars in the Milky Way. It is not close to stellar temperatures. It has crossed them, sitting in a category of the universe apparently reserved for something other than planets. The star it orbits, KLT 9, is itself a young and unusually energetic blue-white star, one of the most radiatively aggressive stellar environments a planet could find itself locked inside. KLT 9b orbits that star in just 1.5 Earth days, tidally locked, one face always forward, absorbing a continuous and unrelenting flood of ultraviolet and X-ray radiation with no rotation to distribute the load. Located 670 light-years from Earth, KLT 9b was identified through the same transit method that has revealed most of the worlds on this list. When a planet passes in front of its star, the light dims by a measurable fraction, and the pattern of that dimming carries information about the planet's size, orbit, and atmospheric composition. What the data returned for KLT 9b was a temperature reading that initially looked like an error in the pipeline. The number was too high, sitting in a range that belonged to stellar physics rather than planetary science. Researchers checked their calculations, verified their models, and arrived at the same conclusion repeatedly. The planet was genuinely that hot, not due to any internal energy source, not due to nuclear fusion, which requires a mass far beyond what KLT-9b possesses, but purely from the relentless incoming radiation of a star cannot turn away from. That distinction matters more than it might initially seem, because it means the heat is entirely external, imposed continuously from outside, with no mechanism available to the planet to reduce or redirect it. The day side of KLT-9b is not generating heat. It is simply absorbing more of it than any planet has a right to absorb, and it has been doing so for as long as it has occupied this orbit. At 4,300 degrees Celsius, the atmosphere of KLT-9b's day side enters a physical regime that has no parallel anywhere else in the catalog of known planets. Temperature at that level does not simply accelerate molecular motion or drive chemical reactions toward new equilibria. It ends chemistry entirely, because chemistry requires molecules, and molecules at that temperature cannot survive. The thermal energy available on KLT-9b's day side is sufficient to break the bonds that hold atoms together into compounds, and it does so without discrimination or exception. Water molecules, which survive intact in the atmospheres of planets far hotter than Earth, are torn apart on KLT-9b's day side. Carbon dioxide, one of the most stable molecular structures in common atmospheric chemistry, is broken down into its component atoms. Even molecular hydrogen, the simplest and most durable diatomic molecule in the universe, cannot hold itself together in this environment. What remains is not an atmosphere in any conventional sense of the word. It is a plasma of individual, unbound atoms, stripped of their molecular relationships, existing in a state that belongs more to stellar physics than to any planetary framework we have developed. The practical consequence of this atmospheric state is something that resists easy description because it has no analog in human experience. Every framework we use to think about environmental danger, heat, fire, chemical exposure, radiation burns, assumes the presence of matter in a form that interacts with biological tissue in recognizable ways. KLT-9b's day side does not offer that. If a human body were somehow transported to the day side atmosphere of this planet, the danger would not arrive in any form the body could register or respond to. Burning requires combustion, and combustion requires molecules to oxidize. There are no molecules on the day side of KLT-9b. Radiation damage requires cellular structures to be disrupted by incoming energy, but cellular structures are themselves molecular, and they would not survive long enough to be damaged by radiation in any conventional sense. The correct word for what would happen is dissociation, the reduction of complex biological matter into its simplest atomic constituents, not through fire, not through chemical reaction, but through the simple thermal destruction of every bond holding the structure together. The body would not experience this process because the neurological machinery required to register experience would be among the first structures to go. There is something philosophically unsettling about a danger that operates below the threshold of perception, that removes the possibility of experience before experience can begin. Most extreme environments we have visited on this list allow, at least in imagination, a moment of encounter, a fraction of a second in which the environment announces itself before it destroys what entered it. KLT-9b's day side does not offer that fraction. The process begins before any signal can travel from the surface of the body to whatever remains of the nervous system, and it completes itself in a time frame that renders the concept of suffering technically inapplicable. This is not a comfort. It is If anything, a different kind of unsettling, the idea of a place so hostile that hostility itself becomes the wrong word for it. Hostility implies a relationship between the environment and the thing it acts upon. KLT 9b's dayside has no relationship with anything that enters it. It simply reduces it to atoms and continues existing exactly as it did before. The night side of KLT 9b presents a different but equally strange picture. Because the planet is tidally locked, the hemisphere facing away from KLT 9 never receives direct stellar radiation, and the temperature there drops dramatically compared to the dayside. Dramatically, in this context, is a relative term. The night side of KLT 9b is still hot by any planetary standard, just not hot enough to atomize matter. The boundary between the two hemispheres is a region of violent atmospheric circulation, where the extreme temperature differential drives winds of extraordinary speed, carrying atomic matter from the dayside toward the cooler night. As that atomic matter moves away from the direct radiation zone, some of it recombines, atoms finding each other again in the relative quiet of the terminator region, briefly reforming the molecular bonds that the dayside destroys. The atmosphere of KLT 9b is therefore engaged in a continuous cycle of molecular destruction and reformation, atoms made and unmade by the rhythm of the planet's locked position relative to its star. Astronomers have been able to detect specific atomic signatures in KLT 9b's atmosphere through spectroscopic analysis, and the list of what has been found reads like an inventory of stellar rather than planetary chemistry. Iron atoms, ionized iron, titanium, barium, and other heavy metals have been identified in the atmospheric data, floating free in a state that would be unremarkable in the outer layers of a star, but is extraordinary in the atmosphere of something classified as a planet. The detection of ionized iron in particular was significant because ionization requires temperatures that, until KLT 9b, were not expected to exist in any planetary context. Each new spectroscopic result from this planet has reinforced the same conclusion, that KLT 9b is operating in a physical regime that planetary science did not anticipate and is still working to fully describe. The instruments were not broken when they returned these readings. The universe had simply produced something that the instruments had never been pointed at before, and the data was exactly as strange as it appeared. The long-term trajectory of KLT 9b follows a path that is by now a familiar shape on this list. The same radiation that makes the planet's dayside uninhabitable is also, over geological time, dismantling the planet itself. Stellar radiation of the intensity KLT 9b receives does not merely heat the upper atmosphere. It drives atmospheric escape, pushing gas beyond the planet's gravitational reach in a continuous outflow that has been measured and confirmed. The rate of atmospheric loss is substantial, and unlike WASP 12b, where the mechanism of destruction is primarily gravitational stripping, KLT 9b is being eroded by pure radiation pressure. The photons of a blue-white star carrying enough energy to launch atmospheric material into space on every pass. The planet is not being pulled apart. It is being blown apart, molecule by molecule and atom by atom, by a star that is simply too energetic for any planet to survive in proximity to indefinitely. The timescale for this destruction is measured in hundreds of millions of years, long enough that KLT 9b still has a substantial future ahead of it in absolute terms. But the direction of travel is fixed and irreversible. Each year that passes removes more of the atmosphere, lowering the pressure, thinning the layers, exposing deeper and denser material to the radiation that will eventually work through it as well. At some point along this trajectory, what remains of KLT 9b will no longer qualify as a gas giant in any meaningful sense. The gas will be gone, dispersed into the space around its star, and what is left will be whatever sits at the center of the planet, the core, compressed and exposed, stripped of every layer that once surrounded it. Astronomers have described this endpoint as a bare planetary core, a cinder at the edge of a star, and that description carries a weight that precise scientific language sometimes manages to achieve by accident. A cinder is what remains after everything combustible has been consumed. It is the shape of something that was once more than it currently is. What will remain of KL-9b in a few hundred million years is an object that has no name yet, because nothing like it has been observed in that final state. A planetary core exposed to direct stellar radiation, orbiting at a distance that permits no atmosphere, no chemistry, no surface process of any kind, just compressed matter in a tight orbit around a star that has already taken everything else. That image, a bare remnant circling in permanent silence, is the logical conclusion of everything KL-9b currently is. The most extreme planetary atmosphere ever documented, the hottest world in the known catalog, the place where molecules go to cease existing, all of it is a stage in a longer process that ends with nothing left to measure. And somewhere beyond that endpoint, somewhere in the catalog of worlds we have not yet visited tonight, there are planets that challenge the senses in entirely different ways, worlds that are not defined by heat, but by something stranger and in some ways more difficult to hold in the mind. The third world on this list announces itself gently, and that gentleness is precisely the point of it. From any reasonable observing distance, HD 189733b presents as a deep and vivid cobalt blue, the kind of color that carries specific emotional weight for any human eye trained on the night sky. It is the blue of open water seen from altitude, the blue of an afternoon sky in early autumn when the air has gone clean and still. Every instinct built into the human visual system over millions of years of evolution reads that color as familiar, as safe, as something that belongs to the category of worlds that support rather than destroy. That instinct was not built for exoplanets, and it fails completely here. HD 189733b sits 64 light-years from Earth, close enough by cosmic standards to have been studied in considerable detail. The color is real, confirmed by direct observation, a genuine property of this planet's atmosphere, as seen from space. What produces that color is not what you would expect, and what lives inside that color is not what anything would survive. The deception is not intentional. The universe does not plan these things, but it is thorough. This planet looks more like Earth than almost anything else in the confirmed catalog, and it is one of the most lethal environments ever documented. The blue of HD 189733b does not come from water. That distinction matters more than it might seem at first, because the entire emotional logic of the color depends on that assumption. On Earth, the sky is blue because water droplets and gas molecules scatter shorter wavelengths of light preferentially, bouncing blue back toward any eye looking up or looking down from orbit. The oceans deepen that impression, reflecting the sky, absorbing red wavelengths, returning blue. The color of Earth from space is a watercolor, an ocean color, a color built from the substance that makes the planet what it is. HD 189733b produces the same color through an entirely different mechanism, one that shares the optical physics, but none of the implications. The atmosphere of this planet is saturated with particles of silicate, microscopic fragments of glass suspended in the upper layers and distributed throughout the weather systems that circle the globe. Those particles scatter blue light by the same mathematical principle that governs Earth's sky, same wavelengths, same scattering angles, same resulting color. The cause is glass, not water. And the difference between those two substances, in this context, is the difference between life and immediate destruction. Silicate particles suspended in an atmosphere are not passive. They do not drift slowly through still air in gentle currents, catching the light and producing a pretty color for distant observers to admire. They move with whatever moves the atmosphere around them. And on HD 189733b, what moves the atmosphere is a wind system of scale that has no terrestrial equivalent worth comparing it to. The fastest sustained surface wind ever recorded on Earth peaked at roughly 400 kilometers per hour, a figure that represents the absolute outer limit of what our atmosphere can generate under the most extreme storm conditions imaginable. That number, 400 kilometers per hour, The kind of wind that strips buildings to their foundations and moves objects that weigh as much as vehicles is approximately 1/22nd of the wind speed on HD 189733b. The winds on this planet reach 8,700 kilometers per hour, roughly 7 times the speed of sound in standard atmospheric conditions. There is no frame of reference in human experience for that velocity, no storm, no weapon, no engineered system that produces sustained airflow at anything approaching that speed. Those winds are not a localized phenomenon, not a storm system that develops in one region and dissipates as it moves into different pressure zones. They are a permanent feature of the planet's atmospheric structure, driven by a temperature differential between the day side and the night side that sits at approximately 260 degrees Celsius and shows no sign of ever resolving. The day side bakes under continuous stellar exposure. The night side cools in permanent shadow, and the pressure difference between those two hemispheres drives air around the planet in a loop that has been running without interruption for longer than Earth has existed as a world. There's no season that calms this system, no axial tilt that redistributes the energy load and gives the atmosphere a chance to settle into something quieter. The wind is not a weather event on HD 189733b. It is the weather, the entire weather, the only weather, a planetary scale storm that circles the globe continuously and carries everything the atmosphere contains with it at velocities that make the word wind feel inadequate for what it is describing. What the wind carries is the glass. Every silicate particle suspended in the atmosphere of HD 189733b is moving at the speed of the wind that holds it, which is to say it is moving at 7 times the speed of sound, horizontally, in a direction that does not change and does not slow. The particles are small, measured in micrometers, not the large shards that the word glass might suggest. But size is not the relevant variable when velocity is this extreme. A grain of sand traveling at 7 times the speed of sound does not behave like a grain of sand. It behaves like a projectile, because at that velocity the distinction between a particle and a bullet is a matter of mass rather than behavior. The impact energy carried by even a microscopic fragment of silicate moving at 8,700 kilometers per hour is sufficient to do damage that larger, slower objects could not accomplish. The physics of high-velocity impact are unambiguous on this point, and they apply regardless of the size of the object delivering the impact. The comparison that comes to mind most naturally is a sandblaster, an industrial tool that uses compressed air to drive abrasive particles against surfaces at high velocity, stripping paint, cleaning metal, etching glass. A sandblaster operates at speeds measured in hundreds of kilometers per hour and is capable of removing material from hardened steel with sustained application. The wind on HD 189733b is not a sandblaster. It is something for which the sandblaster is the closest available reference point, the way a candle is the closest available reference point for describing the sun. The scale difference between the two makes the comparison almost useless except as a starting point for imagination. A sandblaster at close range will lacerate exposed skin in seconds and cause permanent damage to any unprotected surface. The glass storm on HD 189733b would do the same thing at a rate that makes seconds an overestimate of the relevant timescale, and it would do it not from one direction, but from every direction simultaneously, because the atmosphere is the storm, and the storm is everywhere on this planet at once. The surface temperature of HD 189733b sits at approximately 1,000 degrees Celsius, which is a fact that requires acknowledgement, even though it is almost beside the point in context. 1,000 degrees Celsius is the temperature at which most metals soften and begin to lose structural integrity, the temperature at which glass, ironically, becomes workable and fluid. It is a temperature that would reduce any biological material to ash in a time frame too short to describe meaningfully. But in the context of a planet where the atmosphere is made of glass moving at supersonic speed in a continuous planetary storm, the surface temperature feels like a secondary concern, the kind of detail you note after you've already understood that nothing survives long enough to be burned. The heat is lethal. The wind is lethal. The glass is lethal. Each of these properties would be sufficient on its own to make HD 189733b one of the most hostile environments in the documented catalog. Together, they create something that exceeds any single category of danger and occupies its own distinct classification. What makes this world particularly difficult to sit with is the specific nature of the deception it presents. There is something honest about a planet that looks hostile, a world of obvious fire or visible darkness, or a surface that clearly announces its own wrongness. HD 189733b does not do that. It presents itself in the most reassuring color available to a human observer, the color of home, the color of oceans and skies, and everything that the word habitable implies when it is used without qualification. The scientists who first characterized this planet's color knew immediately what they were looking at, but the knowledge did not fully neutralize the response, because the response is not intellectual. It is older than intellect, built into the visual system at a level below conscious processing. The planet looks like somewhere you could go. The data says otherwise, completely and without ambiguity, but the image persists. That gap between appearance and reality is the thing that makes HD 189733b stay in the mind after the other details have settled into memory. The temperature differential driving those winds, 260 degrees between the day side and the night side, is itself a number worth pausing on. 260 degrees Celsius is the difference between liquid water and molten lead. On Earth, the temperature difference between the warmest inhabited regions and the coldest drives weather systems of extraordinary complexity and violence, and that difference is measured in tens of degrees rather than hundreds. The 260-degree gap on HD 189733b is not a weather driver in any sense that the word weather was designed to accommodate. It is a thermodynamic engine of planetary scale, converting the temperature difference between two hemispheres into kinetic energy at a rate that has been running continuously since the planet formed, and will continue running until the star that drives it changes its output. There is no mechanism available to this planet to reduce that differential. No seasonal variation, no redistribution of energy, no process that brings the two sides closer together in temperature. The engine runs at full capacity permanently, and the wind is its output. HD 189733b will continue being exactly what it is for longer than any human timescale can meaningfully contain. It is not a world in the process of being destroyed, not a planet counting down toward an ending, not a temporary condition that will resolve into something more recognizable. It is a stable system, a planet that has found its equilibrium and is maintaining it with perfect consistency across geological time. The glass storm is not an event. It is a state, the permanent condition of a world that happens to look from a sufficient distance like the most familiar and welcoming thing in the known universe. That is the final thought HD 189733b leaves behind. Not the violence, not the temperature, not even the glass, but the image of something that wears the color of home like a mask and has been wearing it without any awareness of the deception for billions of years. The next world on this list offers no such false comfort, no reassuring color, no moment of misplaced hope. Only a darkness so complete it requires a new vocabulary to describe. The darkness that defines the next world on this list is not the darkness of distance or the darkness of shadow cast by something larger nearby. It is a property of the planet itself, built into its atmosphere at a chemical level, operating as a kind of permanent and total absorption that has no meaningful parallel in any material we encounter in ordinary life. Trace 2b sits 750 light years from Earth, and it does something that should not be physically possible for a planet to do. It takes in light and gives almost none of it back. Not because it is far away, not because it is small, but because something in its atmospheric composition drinks photons the way dry ground drinks rain, completely, immediately, without return. The number that defines this world is not a temperature or an orbital period, though both of those matter. It is a reflectivity figure, a single percentage that reframes everything else about the planet. Trace 2b reflects less than 1% of the light that strikes it, and that figure, small as it looks on a page, represents a physical reality that took astronomers considerable time to accept as genuine. The instruments were checked, the models were rerun, the data was handed to colleagues who had not yet formed an expectation about what it should say. Every time, the answer came back the same: a world that absorbs nearly everything and returns almost nothing, sitting in a region of space where light arrives constantly and essentially disappears. To understand what less than 1% reflectivity actually means, it helps to place it against materials that most people have some intuitive sense of as dark. Coal is among the darkest, naturally occurring substances available on Earth, a material so thoroughly associated with blackness that it functions as a cultural shorthand for the absence of color. Coal reflects approximately 5% of the light that hits it. Black acrylic paint, the kind used specifically when an artist wants the deepest, most light-absorbing surface available on a palette, reflects around 4%. These are substances that the human eye reads as the outer boundary of darkness, the point at which color gives way to something that seems to swallow light rather than interact with it. Trace 2b reflects less than 1%, which means it is darker than coal by a factor that makes coal look, by comparison, like something that actively glows. There is no common material, no paint, no fabric, no engineered surface in standard use that approaches the light absorption of this planet's atmosphere. The darkness of trace 2b is not a shade on any scale we use to describe darkness in ordinary contexts. It is a category of its own, sitting below the bottom of any chart a materials scientist would draw. NASA applied a specific phrase to this world when the data was confirmed, and that phrase was the planet of eternal night, a description that the agency does not typically reach for when more precise language is available. The fact that they reach for it here says something about the limits of technical vocabulary when confronted with a phenomenon this extreme. Eternal night implies not merely darkness, but a permanence to that darkness, a condition that does not vary with orbit or rotation or the position of any light source. Because the darkness is not produced by the absence of light, but by the planet's own refusal to reflect it. Light arrives at trace 2b in enormous quantities. The planet orbits its host star in just 2.5 Earth days, pressed close enough that the radiation it receives is substantial and continuous. All of that energy arrives, strikes the atmosphere, and is absorbed. The planet does not redirect it, does not scatter it, does not bounce any meaningful fraction of it back into space. It takes it all in and holds it. And the result is a surface that is simultaneously one of the most irradiated environments in the documented catalog and one of the most visually impenetrable objects we have ever confirmed exists. The consequence of absorbing that much stellar energy without reflecting any of it is a temperature that builds on the day side to approximately 1,000 degrees Celsius. That heat has nowhere to go as light because the planet cannot reflect it, so it goes somewhere else instead. At 1,000 degrees, matter does not simply sit warm and still. It radiates, emitting energy in wavelengths that correspond to its temperature. And at 1,000 degrees, those wavelengths sit at the deep red end of the visible spectrum, just barely within the range that a human eye could theoretically detect under ideal conditions. Trace 2b glows, not with reflected starlight, not with any light it has borrowed from its star, but with its own thermal emission, a faint and deeply dim red produced by the heat that has accumulated in its atmosphere and surface layers. This is not the glow of fire or the glow of a lamp. It is the glow of a coal that has been removed from the flame and is cooling, the last visible evidence of heat that was once much greater, a dim and patient radiation that requires darkness itself to be perceptible. The experience of standing on trace 2b, if such a thing were imaginable, would present a paradox that the human sensory system is not equipped to process without contradiction. The sky above would be absolute black, not the deep blue black of a moonless night on Earth, not the dark of a windowless room, but a blackness with no gradation and no reference point, a visual field that offers nothing to the eye attempting to orient itself. The stars would be invisible, not because they are absent, but because the atmosphere absorbs their light before it can penetrate to any surface below. There would be no horizon distinguishable by color, no ambient glow from any source, nothing that the visual system could use to construct a sense of space or depth or direction. And yet the ground beneath would not be cold. It would be radiating heat at temperatures sufficient to destroy any biological material instantly, emanating that dim red thermal glow upward into the total darkness above it. Darkness and heat together, in a combination that the human mind associates with opposite things, because on Earth darkness means the absence of the sun, and the sun is the source of warmth. Trace 2b decouples those two things entirely and presents them simultaneously, a world that is thermally extreme and visually non-existent at the same time. The mechanism behind this extraordinary absorption is not fully understood, and that gap in understanding is itself worth sitting with for a moment. Science is comfortable with things that are extreme when the physics behind the extremity is clear. A planet that is very hot because it orbits very close to a very energetic star is extreme, but explicable. The chain of causation is intact, and the numbers follow logically from the conditions. Trace 2b does not offer that comfort. The leading theories point to specific chemical compounds in the atmosphere: sodium, potassium, titanium oxide, all of which are known to absorb light efficiently across various wavelengths. But none of the models built around these compounds fully account for an absorption rate this high. The numbers in the models fall short of the numbers in the data, and that gap means something in the atmosphere of Trace 2b is absorbing light by a mechanism or at a concentration that current atmospheric science has not successfully characterized. The planet is darker than our best explanation for its darkness, and that is a sentence that should give anyone who thinks carefully about it a moment of genuine pause. What Trace 2b represents in the broader catalog of extreme worlds is a different kind of wrongness than what came before it on this list. The previous planets were wrong in ways that involved violence, heat that destroyed matter, winds that carried lethal material at lethal speeds, gravity that reshaped solid objects. Trace 2b is wrong in a way that is quieter and in some respects more difficult to hold in the imagination. It does not announce itself through destruction or motion. It simply refuses to participate in the most basic optical transaction that planets are supposed to engage in: the reflection of their star's light back into space. Every other planet we have discussed, every planet in our solar system, every moon, every asteroid, every fragment of rock or ice in any orbit we have ever measured reflects some portion of the light that reaches it. Trace 2b has opted out of that arrangement in a way that no physical model fully predicted, and it has been doing so quietly and completely for as long as it has occupied its current orbit around its host star. The next world on this list requires a shift in register that the mind does not make easily, because what K2-141b presents is not darkness or heat in isolation, but a cycle, a planetary process that mirrors something familiar and then reveals itself to be operating with entirely different materials at entirely different scales. On Earth, the water cycle is so fundamental to the planet's character that it is difficult to think about the surface without it. Water moves, evaporates, rises, condenses, falls, flows, returns. That cycle is the engine behind weather, erosion, ocean circulation, and the distribution of energy across the planet's surface. It is so deeply woven into what Earth is that the word weather, for most people, is implicitly a water story. K2-141b has a cycle of the same structural shape, the same basic logic of evaporation and condensation and return. The substance moving through that cycle is not water. It is rock, and the scale and temperature at which that rock moves through its cycle makes the water cycle of Earth look like something happening in a terrarium. K2-141b sits approximately 200 light-years from Earth and completes a full orbit around its host star in just under 7 hours. That orbital period places it in a category of proximity that makes even WASP 12b seem distant by comparison, pressed so close to its star that the dayside surface temperature exceeds 3,000 degrees Celsius, a temperature at which the distinction between solid rock and liquid rock and vaporized rock is simply a matter of how close to the star you are standing. The entire dayside surface is covered in a global magma ocean, not a localized lava field or a volcanic region, but a continuous ocean of molten rock hundreds of kilometers deep in places, circulating in slow, convective patterns driven by the heat pouring in from the star above. Beneath that ocean, more rock is melting continuously, feeding the surface from below, maintaining the depth and temperature of the ocean against the only force that works against it, which is the violent evaporation happening at the surface, where the heat is sufficient to turn solid mineral compounds directly into gas. The minerals that evaporate from K2-141b's dayside surface, sodium, silicon oxide, silicon monoxide, rise into a thin and extraordinarily hot atmosphere of rock vapor, carried upward by the same thermal energy that produced them. That vapor is then seized by winds driven across the planet by the temperature difference between the 3,000-degree day side and the night side, which plunges to approximately minus 200 degrees Celsius, a differential so extreme that the winds it generates are supersonic, moving rock gas from the lit hemisphere toward the dark one at speeds that compress the atmospheric transit into a time frame measured in hours rather than days. On the night side, where the star's energy does not reach and the temperature drops below any threshold at which rock vapor can remain gaseous, the minerals cool, condense, and fall. Not as rain in any sense that the word was designed to describe, but as particles of sodium and silicate descending from a sky that has no clouds, only the slow precipitation of what was recently a solid surface on the other side of the planet. Those particles collect on the night side surface, accumulate in frozen deposits along the colder regions, and then drift slowly toward the terminator, the boundary between the two hemispheres, where the magma ocean begins and the rock is absorbed back into the cycle, melted again, evaporated again, carried again across the sky, falling again on the dark side, endlessly, without interruption, without variation. A planetary rock cycle that has been running since this world formed and will continue running until the star above it changes or dies. That rock cycle on K2-141b runs without pause, without variation, a machine that has no off switch and no memory. The next world on this list is defined not by what it destroys, but by what it still carries inside itself. A warmth that belongs to its own beginning rather than to anything external imposing heat upon it. GJ504b sits 57 light-years from Earth, a gas giant of unremarkable address in an unremarkable constellation, orbiting a star that resembles our own in most of the ways that matter. Nothing about its location announces what it is. Nothing about the system it inhabits suggests that one of its members is still in the process of becoming itself, still radiating the thermal memory of its own violent assembly, still glowing from an event that happened 160 million years ago and has not yet finished releasing its energy into the surrounding dark. That glow is not borrowed from its star, not reflected, not produced by any fusion or fission or chemical reaction happening inside it right now. It is the leftover heat of creation, the residual warmth of a world that has not yet had time to cool, and it gives GJ504b something that almost no other confirmed planet in the catalog possesses, a color that belongs entirely to itself. 160 million years is a number that resists easy emotional access until you place it against something the mind already holds. When GJ504b formed, the dinosaurs had not yet gone extinct, and they would not for another 95 million years after that. In the timescale of planetary science, where ages are typically counted in billions, 160 million years is not a long history, but a brief prologue, a planet that has barely cleared the opening pages of its existence. Most of the worlds we have visited tonight are ancient by any measure. Their formation energies long since radiated away, Their surfaces and atmospheres shaped by billions of years of processes we can study but not witness. GJ504b is still in the stage that every gas giant passed through, the stage where the heat of assembly has not yet fully dissipated, where the planet is still contracting slightly under its own gravity, still releasing the energy that the collapse of its constituent material converted into warmth. The difference is that every other gas giant in the documented catalog finished that stage long before anything on Earth had eyes to look up at the sky. The temperature at the cloud tops of GJ504b sits at approximately 230 degrees Celsius, a number that would be unremarkable for a planet receiving intense stellar radiation at close orbital range. GJ504b is not at close range, and the heat is not coming from outside. It is radiating outward from within, driven by the slow release of gravitational potential energy that has been stored in the planet's interior since the moment its formation completed. That internal heat source produces something that no amount of reflected starlight could replicate, a genuine thermal emission from the planet itself, a glow that is the planet's own rather than the star's energy returned. The color that emission produces sits in the magenta range of the visible spectrum, a deep and vivid pinkish purple that photographs as distinctly, unambiguously pink against the neutral background of surrounding space. We have actual images of this world, direct photographs taken by telescopes capable of resolving the planet as a separate point of light beside its host star, and in those images it appears exactly as described, a small bright pink, sitting in the dark, self-illuminated, announcing its own youth in the only language a planet has available to it. GJ504b has a mass 4 times that of Jupiter, which is a figure that requires a moment to fully register, because Jupiter itself is already a figure most people have not fully registered. Jupiter contains more than twice the mass of all the other planets in our solar system combined, a gas giant so large that it influences the orbital mechanics of everything else in its neighborhood. GJ504b is 4 of those. Its gravity at the cloud tops is approximately 10 times what you experience standing on the surface of Earth, a figure that places it well outside the range of anything human physiology was designed to function within. The cardiovascular system that keeps a human body operational was built for one gravity, calibrated over millions of years of evolution to pump blood from the heart to the brain against a specific and familiar downward pull. At 10 times that pull, the heart cannot win that contest. Blood does not reach the brain in sufficient quantity, and the body begins to fail from the top down, the most oxygen-dependent structures going first, the rest following in a sequence that takes minutes rather than hours. The planet is not hostile in the way that a storm is hostile or a fire is hostile. It is simply operating at a scale that human biology was never equipped to encounter. What GJ504b represents in the catalog of extreme worlds is something philosophically distinct from everything that preceded it on this list. The other planets we have visited are defined by what they do to things that enter them, by the violence or the darkness or the heat or the pressure they impose on anything that approaches. GJ504b is defined by what it is doing to itself, by an internal process of gradual transformation that is moving in only one direction and cannot be reversed or accelerated. It is cooling. That is the entirety of its trajectory, a slow and continuous loss of the heat that currently makes it visible, a dimming that will proceed across millions of years until the magenta glow fades to something dimmer, then to something only instruments can detect, then to nothing that distinguishes it from any other cold gas giant orbiting any other unremarkable star. In a billion years, GJ504b will look entirely different from what it looks like now, darker, colder, reflecting its star's light rather than producing its own. Just another point of light in a catalog that already contains more points of light than any mind can hold. The photograph we have of it now is a portrait of a moment that will not repeat. There's a planet 41 light years from Earth that was, for a brief period in the early years of this decade, the most discussed object in the history of planetary science. Not because of what it was doing, but because of what scientists believed it was made of. 55 Cancri E is a rocky super-Earth, twice the size of our planet, orbiting its host star in just 18 hours, a year so short that the concept of a year loses its meaning entirely on this world. It was studied extensively before 2012, cataloged and characterized in the way that thousands of exoplanets have been cataloged and characterized, its mass and radius measured, its orbital parameters confirmed, its surface temperature estimated. Then a more detailed analysis of its composition was published, and the conversation around it changed completely. The mass and the radius, taken together, pointed to an interior unlike anything in our solar system. A world whose bulk composition was consistent with carbon compressed under enormous internal pressure into its most stable and densest crystalline form. The conclusion was not offered tentatively. The numbers kept returning the same answer. The interior of 55 Cancri E, the analysis proposed, was made primarily of diamond. Not diamond-bearing rock, not a planet with diamond deposits scattered through its interior the way Earth has carbon deposits scattered through its own. The proposal was a planetary interior of compressed crystalline carbon sitting beneath a thin graphite crust. A structure in which the most valuable mineral humans have ever assigned a price to was not a rare find, but the dominant material, the bulk of the world, the substance that everything else sat on top of. The star this planet orbits, 55 Cancri, is visible to the naked eye on a clear night from Earth, close enough and bright enough to appear on standard star charts without any optical aid. The most diamond-dense object ever proposed in the history of planetary science orbits a star you can see by simply stepping outside after dark and looking in the right direction. That juxtaposition, the accessibility of the star and the inaccessibility of everything about the planet, is one of the more quietly unsettling facts in the catalog of extreme worlds. The story around 55 Cancri has grown more complicated in the years since that initial analysis, as the story around any scientific discovery tends to do when more instruments are pointed at it and more models are applied to the data. Later work suggested that the carbon diamond interpretation may have been an oversimplification, that the planet's interior chemistry could involve other high-pressure mineral structures not fully accounted for in the original models. The scientific consensus has shifted toward a more ambiguous picture, a world whose interior is genuinely unusual, but whose exact composition remains contested and unresolved. What has not shifted, what every model and every dataset agrees on regardless of what assumptions are made about the interior, is what the surface of this planet looks like right now, today, in its current state. 55 Cancri E orbits its star in 18 hours, tidally locked, one hemisphere in permanent stellar exposure, and the surface temperature on that exposed side reaches approximately 2,400 degrees Celsius. At that temperature, the surface is not rock in any sense the word is designed to describe. It is a global ocean of lava, deep and churning, covering the entire sun-facing side of the planet in a continuous molten sheet. Above that lava ocean, the atmosphere is not empty. Silicate rock vaporizes from the surface at those temperatures and rises into the layers above, forming clouds of glowing mineral vapor that catch the light of the star and reflect it back downward onto the surface below. The star itself, seen from the surface, if anything could survive there to see it, would fill an enormous portion of the sky, sitting less than 2 million kilometers away, close enough that its apparent diameter would dwarf anything in the visual experience of any observer standing on any world in our solar system. The sky above the lava ocean shimmers with reflected heat, silicate vapor glowing in the light of a star that is almost close enough to touch, and beneath that sky the ocean churns in convective patterns driven by the heat pouring in from above. Beneath the ocean, if the original models hold even partially, the most compressed mineral structure in the known universe sits in permanent inaccessibility, wrapped in fire, sealed under a depth of molten rock that no instrument we have built or imagined building could reach. 41 light years away, visible to the naked eye on a clear night, the most valuable object ever proposed sits inside a world that makes its own surface uninhabitable in every direction simultaneously. For most of human history, Jupiter served as the outer boundary of the imagination when it came to planetary scale, the largest thing a planet could be before it became something else entirely. Every exoplanet discovered in the era of modern astronomy was measured against it, described in terms of how many Jupiters it resembled, how many Jupiter masses it carried, how many Jupiter radii it spanned. Jupiter was the unit because Jupiter was the limit, the ceiling of the category, the thing beyond which the word planet gave way to other words. ROXS 42b, located approximately 460 light-years from Earth in the constellation Ophiuchus, requires that ceiling to be removed and the category to be rebuilt around something larger. Its radius is approximately 2.5 times that of Jupiter, possibly more depending on which model is applied to the available data. Its mass sits somewhere between 6 and 9 Jupiter masses, a range that places it in territory where the boundary between a very large gas giant and a brown dwarf, a failed star, sits only a few Jupiter masses further along. That boundary is 13 Jupiter masses, the threshold at which an object becomes massive enough to initiate deuterium fusion and enter the category of stellar rather than planetary physics. ROXS 42b sits below that threshold, probably, but the distance between where it sits and where stars begin is not the comfortable margin that the word planet usually implies. Jupiter sitting in the atmosphere of ROXS 42b would register as a moon. A large one perhaps, but a moon nonetheless, a secondary body orbiting within the cloud layers of something so much larger that the comparison loses its original meaning entirely. The gravity at the cloud tops of ROXS 42b is estimated at somewhere between 5 and 8 times Earth's, a range that reflects the genuine uncertainty in the mass estimates, but that in either case describes an environment where the atmospheric pressure builds with depth at a rate that has no analog in our solar system. The internal pressure at whatever serves as the core of this object, if a discrete core exists rather than a gradual compression gradient, would exceed anything that material science has characterized or any laboratory on Earth has produced. ROXS 42b orbits its host star at a distance roughly 157 times the distance between Earth and the Sun, far beyond any region where standard planet formation models predict that a body of this size could have assembled itself from a protoplanetary disk. Something in the history of the system did not follow the standard script. And whether ROXS 42b formed the way planets form or collapsed directly from a gas cloud the way stars form remains genuinely unresolved. What is resolved is the scale, and the scale does what extreme scales always do. It makes the familiar unfamiliar. It takes Jupiter, the thing we called enormous, and reduces it to a footnote beside something the universe apparently decided to build without consulting any of our categories first. Everything we have visited tonight has been defined by excess, by heat that destroys matter, by darkness that swallows light whole. The next two worlds demand a different kind of attention, one quieter and one so vast it breaks the imagination. They sit at opposite ends of what extreme can mean when applied to a planet. One is almost familiar, almost home, almost the thing we have been looking for across the entire documented catalog of worlds. The other carries a structure so enormous that our solar system cannot contain it even as a thought experiment. Together, they form the final chapter of this particular tour of the universe's more unsettling achievements. One will make you feel the specific grief of distance, the particular ache of something known but unreachable. The other will leave you standing in the dark with something turning slowly overhead that has no name adequate to what it is. We begin with the one that looks most like the place you're sitting right now. And we begin with the fact that looking like home and being home are separated by a distance that has no human solution. Kepler 442b orbits a star slightly smaller and cooler than our own, a K-type star that burns with less aggression and considerably more patience than the Sun. The planet itself is rocky, the same broad category as Earth, a world with a solid surface rather than a gas envelope surrounding an ambiguous interior. Its size is estimated at approximately 1.3 times Earth's diameter, close enough to our own dimensions that the difference would be noticeable but not disorienting to any instrument we have built to measure such things. It receives about 70% of the solar energy that Earth receives from our Sun, a figure that places it comfortably within the range where liquid water could exist on a planetary surface. The star it orbits is quieter than ours, less prone to the flares and radiation events that can strip atmospheres from planets sitting in otherwise hospitable positions. Everything about this world, taken measurement by measurement, points in the same direction toward a planet that has not violated any of the conditions we associate with habitability. The Earth Similarity Index is a scientific instrument in the form of a number, a single value between 0 and 1 that attempts to compress everything measurable about a planet's resemblance to Earth into a single comparable figure. It accounts for size, density, temperature, and the energy environment provided by the host star, weighting each parameter against what Earth offers and returning a score that allows worlds to be ranked against one another in terms of how closely they match the conditions we know can support life. Most confirmed exoplanets score well below half on this index, their conditions diverging from Earth's in one or several ways that push the number down toward the uninhabitable end of the scale. Kepler 442b scores 0.84 out of 1.0. The highest score of any confirmed exoplanet in the documented catalog. No other confirmed world has come closer, by this measure, to being what Earth is. That number is not a guarantee of anything, not a confirmation of life, or oceans, or breathable air, or any specific feature we associate with home. It is a statement about resemblance, and the resemblance it describes is the closest we have ever formally confirmed exists anywhere in the universe beyond our own world. Kepler 442b is 1,260 light-years from Earth, and that number requires a specific kind of translation to mean anything at all. The Parker Solar Probe is the fastest object humanity has ever successfully launched, a spacecraft that uses the gravity of the Sun itself to accelerate to speeds approaching 690,000 kilometers per hour. That speed is incomprehensible by any terrestrial standard. Fast enough to circle Earth more than 17 times in a single minute. Fast enough to reach the moon in roughly 20 seconds. At that speed, traveling without stopping, without slowing, without any of the gravitational assists and orbital mechanics that make the probe's actual trajectory so complex, the journey to Kepler 442b would take approximately 1.9 million years. That figure is not a challenge to be engineered around or a problem waiting for a sufficiently clever solution. It is a statement about the structure of the universe, about the relationship between the distances that exist and the speeds that matter is capable of reaching. There is no propulsion concept on any drawing board in any research institution at any level of theoretical development that reduces that journey to a human timescale. Not ion drives, not solar sails, not any proposed variant of nuclear propulsion, not any theoretical framework that currently exists in the scientific literature brings the travel time to Kepler 442b within the span of a civilization, let alone a human life. The planet is confirmed. Its properties are measured. Its score on the index of similarity to Earth is the highest number ever recorded for a world beyond our own. And it is as unreachable as if it did not exist, because the distance between knowing something is there and being able to go there is, in this case, a gap that physics as we currently understand it cannot close. Somewhere out there, 1,260 light years from where you're sitting right now, there may be a sky above a rocky surface, clouds forming over liquid water, conditions assembling themselves into something that would feel, to any mind capable of standing in it, like the most natural thing in the universe. We will almost certainly never know. That distance is its own category of experience, distinct from the violence and heat and darkness that defined the earlier worlds on this list. The previous planets were hostile, environments that destroyed things, places where the danger was immediate and total and physical. Kepler 442b is not hostile. It is simply far, and far, in this case, means something that no human institution has the capacity to address. The grief that distance produces is quieter than the response to something dangerous. But it has a different quality to it, the specific weight of something that is not threatening, but is permanently, structurally out of reach. Most things that are out of reach for reasons that feel contingent, reasons that could change with sufficient time or technology or resources. The distance to Kepler, 442b, does not feel contingent. It feels like a law, like the kind of fact the universe states once and does not revise. We know it is there. We have measured it carefully. And we will sit here 1,260 light years away, knowing. The final world on this list requires abandoning every scale we have used tonight and building a new one from scratch. J1407b orbits a young sun-like star approximately 434 light years from Earth, a star designated J1407 in the catalog of systems that have been surveyed by the SuperWASP program. In 2012, astronomers analyzing the light curves from that survey noticed something that had no precedent in the existing data. When J1407b passed in front of its host star, the star's light did not dim by the fraction of a percent that a planet transit typically produces. It dimmed by 95%, a figure so far outside any expected range that the initial response was to examine the equipment before accepting the number as real. Jupiter, passing in front of a star, blocks approximately 1% of the star's light. Whatever was crossing J1407 was blocking nearly all of it, and the pattern of that dimming, the way it faded and held and faded again across different wavelengths, carried information that astronomers spent months working backward through to reconstruct what had caused it. What the data described was a ring system, but the word ring system belongs to a different order of magnitude than anything Saturn or any other planet in our solar system has ever offered. The ring system of J1407b spans approximately 120 million kilometers in diameter, a structure so large that placing it in our solar system requires reference points drawn from planetary orbits rather than planetary sizes. Venus orbits the Sun at a distance of approximately 108 million kilometers, and the rings of J1407b, centered where J1407b sits, would extend beyond that orbit in every direction. Saturn, with its celebrated and beautiful ring system, would sit at the center of J1407b's rings and be entirely contained within their innermost bands, the outer edges extending so far beyond it that Saturn itself would be invisible against the scale of what surrounded it. The rings are not uniform. They're organized into at least 37 distinct bands separated by gaps, and at least one of those gaps shows signs of material being cleared from it, the early signature of a moon forming inside the ring structure exactly as the moons of our solar system formed from the early solar disk. If J1407b occupied the position in our solar system that Saturn currently holds, and you stepped outside on a clear night and looked up, the ring system would span an area of sky more than 10 times wider than the full moon appears to a human eye from Earth. Not 10 times brighter, not 10 times more impressive in some abstract sense, but 10 times wider across the actual field of vision, a structure that would dominate the night sky the way nothing else in human astronomical experience has ever dominated it. The question of what J1407b actually is remains genuinely unresolved in the scientific literature. Some researchers maintain that it is a planet in a stable orbit around its host star, its ring plane tilted at an angle that prevents subsequent transits from being detected. Others have proposed that it may be a freely drifting sub-brown dwarf, a failed star with a protoplanetary disk that happened to pass between Earth and J1407 in a cosmic coincidence that the data captured and will not repeat. What is not in question is the ring system itself, the structure that crossed between us and that star in 2012 and left its signature in the light curve data for any instrument pointed at the right coordinates to read. Whatever J1407b is, planet or drifting substellar object, or something the existing categories do not fully accommodate, it carries with it a disk of material more vast than anything else in the documented universe. 37 bands of rock and ice and dust turning slowly around a center that may or may not be bound to any star at all. If it is drifting freely, it is out there now, somewhere in the dark between the stars, carrying its impossible rings through interstellar space with no sun to orbit and no system to belong to, a structure the size of a planetary orbit, moving silently through a void that has no edges. Tonight, after everything this list has contained, after the egg-shaped planet bleeding into its star and the world hotter than 80% of all known stars, and the glass storm that wears the color of home, and the planet that drinks light and gives nothing back, and a world where rocks evaporate and fall as rain, and the newborn giant still glowing pink from its own creation, and the diamond world wrapped in lava, and the object so large that Jupiter would be its moon, and the planet that scores highest on every measure of resemblance to Earth and sits forever beyond any reach we will ever have. The final image the universe offers is this. Somewhere out there, those rings are turning. Step outside tonight. Let your eyes adjust, find the stars pressing through the dark above you, and hold that thought. The universe built something out there that exceeds every boundary we drew for it. And it is still out there, still moving, still real, whether or not anything with a mind ever finds it.